Hello and welcome to this video on which method should I use to solve a quadratic equation. Alright, so over the past few videos and in many videos before that as well a while back, we've seen plenty of quadratic equations and gone over many different ways of solving them. There was you could solve a quadratic equation by factoring, by the use of the square root property, through the method of completing the square, or with the quadratic formula. So what I have here for you today are a couple pages where I just go over what I feel are the most efficient methods to solve quadratic equations that look a certain way. And then I'll go into a few examples after that where I use, again, what I feel is the most efficient method. Now, as mentioned, there are several methods you can use to solve a quadratic equation. So if you like one over the other, you like completing the square over the quadratic formula, you choose, right? You decide which one you like best and go from there. This is just a video on my personal preferences, okay? But I hope it helps you. All right. So in my first couple pages, just have a little table here. It's already pre-written. Where on the left side, I have the different forms a quadratic equation could take, or any quadratic equation could be written in one of these forms. And then on the right side, I have what I feel would be the most efficient method for solving that quadratic equation. So on this page, I have, a quadratic equation of the form x squared, the variable squared equals some number, right? P is any real number here. Or, some number a times the variable squared times x squared plus another number c equals 0. Or some quantity with ax plus b, where a and b are numbers, x is the variable here. That is all inside this square, right, in the base of this power of 2, and then equals some number p on the other side. And what you might notice about every single one of these, and I had brought this up in the video on the use of the square root property, in every single one of these, notice that there is a variable inside a square, and I'll say inside, right, in the base of a square, right? The variable x is in the base of this square. Here the variable x is in the base of this square. Here the variable is in the base of this square. There's in each one of these, there's a variable inside of a square and no variable, right, no x being the variable here, no variable outside the square. So again, look, there's x in the base of this square, no x's outside the square. Same for this, right? So if you're seeing that, if you're seeing a variable in the base of a square and no variable outside that base, then you should be able to use the square root property. Remember how to use the square root property. You get the equation into this form where you have the square alone, right? You isolate the square, and then some real number, which is I'm representing by n here, some real number on the other side. Then the value of this base, right, the x, is either the principal square root of n, the positive square root of n, or the value of x could be the negative square root of n, and this would be a true statement. And then you would solve these equations separately, and then of course check your solutions. All right, and if you're unfamiliar again with the square root property, please look up the video I put up or somebody else's video on use of the square root property. Okay, Next page. And in both of these, I have the quadratic equation in standard form, right, where the quadratic polynomial is on one side and 0 is on the other. So ax squared, plus bx plus c equals 0. So here you see I have a variable inside a square, right? But there's also a variable, the x, outside that square. So the use of the square root property wouldn't be very efficient here. You wouldn't be really able to get anything. Now you can use the complete the square method to rewrite these equations in a way that you can use the square root property for. Right? Again, look up a video on completing the square, right? Solving a quadratic equation by completing the square. But what I'm going to do in these cases, right, if you can write your quadratic equation in standard form like this, we're going to check what's called, and I've had this up in again a prior video, we're going to find the value of this b squared minus 4 times a times c, right, where b, a, and c are just the coefficients of the quadratic polynomial here in standard form. This b squared minus 4ac, if you recall, was called the discriminant of the equation. All right, so I find the value of the discriminant, and if the discriminant is a perfect square, right, so it's like 1 or 4 or 9, 16, right, perfect squares. If the discriminant is a perfect square, that means that your two solutions will be rational numbers, and you should be able to solve by factoring. Alright, so you get everything to one side, 0 on the other. You factor this polynomial, the quadratic, into the product of two linear factors, and then basically separate them, by the use of the zero product property. All right, remember, if a product is equal to 0, then one of the factors must be 0, and you go and solve each of those equations. Now, sometimes the numbers are large, so I'm saying the factoring method would be efficient here if the quadratic is, easy to factor. If the numbers are relatively small and you can figure out factors of these numbers rather quickly. But if the numbers are very large, factoring might not be the easiest thing to do. So I would say otherwise, right, if factoring is not very easy to see, use the quadratic formula. Right, it's very simple to jump to the quadratic formula for the solutions of an equation that's in this standard form. So recall what that was. I wrote it up again here. If I have an equation, a quadratic equation in standard form, then its solutions, the values of x will be, the opposite of b, plus or minus, right? That means one with the plus, one solution with the minus, the square root of the discriminant. Right, so again, the quadratic formula is nice to use. If I found the discriminant earlier, then you already know the value of the expression underneath the radical symbol, underneath the square root, right, the radicand. So negative b plus or minus the square root of the discriminant, b squared minus 4ac, and then everything up there, all of it, right, so big long fraction bar is in the numerator, and all divided by 2 times a. All right. Okay, and then lastly, this was the case when the discriminant is a perfect square, right? 1, 4, 9, 16, 25, etc. Well, what if the discriminant is not a perfect square, or the discriminant b squared minus 4ac, what if that's a negative number? If you recall, when the discriminant is not a perfect square, but still positive, so like 2, 3, 5, 6, 7, 8, then the equation is going to have two irrational solutions, two real number irrational solutions. And if the discriminant is negative, right, negative 1, negative 8, negative 28, whatever, then you're going to be taking the square root of a negative number in the quadratic formula, right? When you find your solutions, remember the square root of a negative number is one of those pure imaginary numbers. So you're going to have two complex solutions that aren't real numbers. Right? They'll have a non-zero imaginary part to them. So in either of these cases, when the discriminant is not a perfect square, or when the discriminant is negative, I'd say, you can, if it's in standard form, you can jump to the quadratic formula, use that very quickly. Or if, and I say easy looking, right? I'd say, if the coefficients of A and B are maybe multiples of one another, say A is 2 and B is 4, or maybe if A is 1 and B is even, right? And if A is 1 and B is 6 or something like that. There are certain cases when the completing the square method would be very easy to do. But if the coefficients are all some really crazy, like a half for A and 2/3 for B and -5/7 for C, I mean, either one of these will be difficult, so I would recommend just using the quadratic formula. If it looks more difficult to complete, then it won't be worth your time, to try and complete the square and possibly mess up, when you can just go into the quadratic formula. Now, if there are fractions, this will be kind of ugly, but I think most people find it easier to simplify when it's already set up in a nice sweet formula for them like that. Okay, and every quadratic equation should be able to be written in this standard form or in one of these forms here. Okay, so let's go into I have a few examples where I'm going to solve the equation using an appropriate method. So here, for the rest of the examples in this video, the instructions are the same. I'm asked to solve each quadratic equation using any appropriate method. Alright, so the first equation I have here is 5 times n squared minus 45 equals 0. Now, you can do this again, like I said, this is just how I would prefer to do it. You can do it other ways if you want. In fact, I'll show you a couple ways to do this first one. Now notice it's in that standard form, right? Everything's on one side, 0 on the other. But notice there's a variable in a square, right? N to the second there. But there's no variable outside that square. So what I'm going to do is I'm going to use the square root property to solve this. Alright, so how we do that is first we isolate the square. Alright, so the square here, right, the only thing being squared is this variable n, right? This is the square, right? Not the 5. The 5 is not in parentheses with the n, right? So this is the square. So I'm going to isolate that. Right? So first I would be adding 45 to both sides, trying to get the n squared alone. Right? So then we'll have 5n squared on the left equals, and then 0 plus 45, positive 45 on the right. Right? And it's still, the n squared, the square is still not isolated. So now I'm going to be, it's being multiplied by 5, so to undo that I would divide by 5 or multiply by 1/5. Right? So I divide both sides by 5, giving me the n squared equals, and then 45 divided by 5 is 9. Okay, so now I have what I want. I can now apply the square root property to this. Right? I have this isolated square alone equals some number. So then by that square root property, the value of the base n is either the positive square root of that number 9, or the base n is equal to the negative square root of 9. But we know what the principal square root of 9 is, right? That's 3, right? 9 is 3 squared. So either n equals 3 or n equals -3. And don't forget to check your solutions at the end. Always, when solving an equation, check your solutions back in the original equation, right? Back in the way it originally looked. So I can do these pretty quickly here. If n is 3, putting that in for n, 3 squared is 9. 5 times 9 is 45. 45 minus 45 is indeed 0. So 3 is a good solution. -3, same thing. When you take -3 and square it, right, -3 times -3, it's +9. Times 5 would be 45. Minus 45 would again indeed be 0. So both of these are valid solutions. I'll circle them. Right? They're both good. And again, since both of these look exactly the same, except one is a plus, one is a minus, right? You might see the solutions written out like this, plus or minus 3, just to condense things. But this statement here means the same thing as this, right? N equals +3 or n equals -3. Both are good solutions. Right. So again, that's how I would have preferred to do it, because I noticed I had this variable in a square and no variable outside the square. I would isolate that square and use the square root property. Now, as I mentioned, you don't have to do it the way I'm doing it. There are other ways to do this. I mean, I could use the quadratic formula, right? A is 5, B would be 0, right? Remember, B is the coefficient of the first powered term, and there is no n to the first power. So A is 5, B is 0, and then the C, the constant term, would be -45. And then I plug those into the quadratic formula and simplify, right? You could do that as well. I'm not going to do that, though. I mean, -45 is a reasonably large number for me, so I'd rather not do that at the moment. But we could also do factoring pretty easily. All right, so here we go again. Because look at this, right? I'll show you that you can use factoring for this. I can find, it's in standard form, right? It's in standard form. So let's find the value of that discriminant, right? The b squared minus 4ac. I already mentioned, remember, b is 0. So 0 squared minus 4 times a is the coefficient of the squared term, so +5, times c is the constant term, right, -45. So I have 0, and then you have a negative times a positive would be a negative, and then times a negative again would be a positive. Right? So plus. Now 4 times 5 is 20, and then 20 times 45 would be 900. And 900 is actually 30 squared, right? That is a rational number squared. This is a perfect square. That means we should be able to factor. That means we can solve by factoring if we want as well. Alright, but like I said, it wouldn't be the most efficient for me. I would have done it with the square root property, as you saw. So in factoring this, right, well, remember the first thing to look for when factoring a polynomial is the greatest common factor of all the terms. So 5n squared and -45, 5 would go into those evenly. Factor out 5. And if I remove a factor of 5, what you're left with is n squared minus 9. All right, that's 5n squared minus 45 if I were to redistribute. And then n squared minus 9, that's actually one of those differences of two squares, n squared minus 3 squared. So that factors to, remember, n minus 3 multiplied by n plus 3, or n plus 3 times n minus 3. Same thing. And now that I have what I want, I have a product equal to 0. Well, the only way a product of numbers is equal to 0 is if one of those numbers is actually 0 themselves. So either 5 is equal to 0, but that's not true. You're not getting anything from that. 5 can't be 0. Or the other number, one of the other factors, the n minus 3 could be 0. And from this equation, I'm getting the fact, I would add 3 to both sides. We get a possible solution of n equals positive 3. Or this other factor, n plus 3. That could be 0. And then subtracting 3 from both sides, solving that for n, we get n equals negative 3. So what we're getting here is n equals 3 or n equals negative 3. And I already had those up on the previous page. You check them back in the original equation. They both work. Okay? Great. Yeah, and I guess if you wanted to use the quadratic formula, now that I know what b squared minus 4ac is, that would be easy as well. You'd have the opposite of b, or 0, then plus 30, right, the square root of 900, divided by 2 times a. Well, 2 times a would be 10. So you have 30 divided by 10, or 3 as one solution. And then you have the negative b, 0, minus the square root of 900, minus 30 divided by 2a, divided by 10. And minus 30 divided by 10 would be negative 3. So I'm getting these two solutions again if I use the quadratic formula, right? It shouldn't matter what method you use. You'll end up with the same solutions, right? If you're doing things correctly, if you actually got the correct solutions. Wonderful. All right, my next example. All right, now this time I'm just going to pick one method and run with it. Like I said, though, you can, if you like another method better and you find it more efficient for you, do it. All right, you end up with the same solutions anyway. All right, so here I'm solving this equation. Negative 2y squared plus 5y minus 6 equals 0. All right, so it's in that standard form. It's in that, everything's on one side, 0 on the other. A times y squared plus b times y plus c equals 0. So when it's in standard form, I'm going to check the discriminant, that b squared minus 4ac. Alright, so I didn't do this last problem, but let me identify them this time. In this equation, the way it looks right now, the value of that a would be the coefficient of y squared is negative 2. The value of b, positive 5, right, the coefficient of y to the first. And the value of c, right, the constant term without a y attached, is negative 6. Don't forget the negatives are part of the term. Alright, so popping these into the discriminant, right, the b squared minus 4ac. B squared, I have 5 squared minus 4 times a is negative 2 times c is negative 6. 5 squared is 25. And then here I have a negative times a negative times a negative. That'll end up being negative, right? Because a negative times a negative is a positive, and then a positive times a negative is a negative, right? And then 4 times 2 is 8. 8 times 6 is 48. All right, so I have 25 minus 48. So this is a negative number, right? Negative 23, actually, right? So I have a negative discriminant. That means that this equation is going to have two solutions that are, not real. They'll have an imaginary part to them, the square root of a negative number. Alright, so remember I put this up on a prior page. If the discriminant, this b squared minus 4ac, is negative, I'm just going to jump straight to the quadratic formula. Alright, so I'll just put QF for the quadratic formula, okay? So by the quadratic formula, I have my equation in standard form here. The value of y will be equal, and I'll write it out, the opposite of b plus or minus the square root of the discriminant, b squared minus 4ac, and then all of that divided by 2 times a. Right, that's an a, sorry. Alright, well, let me put these numbers in. So the opposite of b, well, that'd be the opposite of 5, so negative 5 plus or minus the square root. Now I already did b squared minus 4ac over here, so I know that the value underneath this square root symbol is negative 23. And then all of this divided by 2 times a. Well, a is negative 2, so 2 times a will be negative 4. Alright, and I've mentioned this in the past, right? When you see the square root of a negative number, remember, you should automatically think, I need to immediately write this as a pure imaginary number, right? A number involving that I. Remember, I is the square root of negative 1, the imaginary unit. So I still have negative 5 plus or minus, and then this square root of negative 23, when I write it as an imaginary, is the square root of positive 23, then afterwards, not inside the root, times I. But very often they'll throw the I, the times I, in front of the radical symbol, just like other variables, but even though I is not a variable. And then all this divided by negative 4. Okay, and then this, simplify the radical. Square root of 23 is as simplified as it can get. Right? There are no perfect squares other than 1 that go into 23 evenly. And then simplify the fraction. Okay. Now, the two terms in the numerator don't have a common factor, other than 1 or negative 1. 1 and negative 1 go into every integer, right? Go into everything. And the denominator, is just negative 4, right? There's no factor of 4 up here in these terms, so you could consider this simplified. It's just very often you'll see that most textbooks, they won't like having a negative number in the denominator. Again, this isn't wrong, right? There is nothing wrong with this. I will circle it, right? So my two solutions are negative 5 plus I times the square root of 23, all divided by negative 4. And my other solution is negative 5 minus I times the square root of 23, all divided by negative 4. And again, don't forget to check them, and I'll leave that to you because it can be kind of tedious. Or use a calculator that has the that allows you to punch in an imaginary unit, as you've seen me do in other videos. But don't forget to check. These should work. I feel like I know I did everything correctly here. But like I said, very often they don't want negative numbers in denominators, right? So or a negative lead in the denominator. So if I just simply multiply, the numerator and denominator of this by negative 1. Now up top, that'll involve some distributing because there are multiple terms. So we could then also say that y equals, when I multiply the numerator by negative 1, I'll have negative 1 times negative 5, that's positive 5. And then, negative 1 times the positive I root 23, that'd be negative I root 23. And then negative 1 times the negative I root 23 would be positive I root 23. Okay, so you can, this minus plus, you could flip this and it would mean exactly the same thing. This just means that one solution is going to have a plus, the other one's going to have a minus, right? So minus or minus, they mean exactly the same thing. Right? And then all of this divided by, and then when I multiply the denominator by negative 1, I have, positive 4. All right. So you can write it like this as well. And I guess one other way we could write these solutions, is in the complex form. All right, remember the way any complex number can be written is a plus bi, right? Some real number plus some pure imaginary number. So if we go through and divide each term up in the numerator by 4, this is one last way to write this. I could say y equals 5/4, plus or minus, minus or plus. Same thing again, plus or minus, minus or plus means it's just the same thing, that one solution has a plus, one solution has a minus. And then the I times the square root of 23 over 4, right? That's the square root of 23 divided by 4. There's your real number times the I in the numerator, right? So you might see solutions written out this way a lot in textbooks as well, where it's in that complex form where you have it as a real number, then plus or minus, and then some pure imaginary number, right, which is a real number times I. Okay, so a lot going on there. I know most of it was about simplifying after I used the quadratic formula, right? That was the hardest part. All right, so when an equation's in standard form like this, typically unless you can see it can be factored, like I mentioned earlier, if you see that, oh, this can be factored really easily, then just solve by factoring. But if you can't see that right away, or you just don't feel like it, do the discriminant first to see what kind of solutions you're going to have, and that'll help dictate what method would be easiest to use to solve. Alright, so I have one final example. So here I have 3 times w squared plus 2 times w equals 5, and we're solving for w. Now there's a variable in a square. There's also a variable outside the square. So I'm not going to use the square root property here. All right. So first thing I'm going to do is put it in a very good form, that very useful form for a quadratic equation, the standard form, right? Take everything to one side and 0 on the other. So I'm going to subtract the 5 from this side and do it to the left side as well. So now on the left side, I have 3 times w squared plus the 2w, and then the negative 5 minus 5 equals 0. Alright, so now I'm in standard form, and again, I personally see that this will be able to be factored. Again, if you don't see that, let's find the discriminant. All right, and that can't hurt. So now that it's in standard form, let me identify these coefficients, the a, the b, and the c. A is the positive 3, b is positive 2, and c is negative 5. All right, and then the discriminant, b squared minus 4ac, all right, would be 2 squared minus 4 times 3 times negative 5. 2 squared is 4. Then this is 60. Right? Negative times negative is positive. 4 times 3 times 5 would be 60. That's 64. That's a perfect square. Right? 64 is 8 squared. And because this is a perfect square, that means we can factor this polynomial. Now, I have put up a video in the past, and you can look up other ones if you want, on factoring quadratic polynomials, that look like a times x squared plus b times x plus c, but instead of x I have w here. So remember how that works. First you can do it by guessing and checking, right? A little guess and check method, a little tedious that. Or remember, I take the lead coefficient 3 times the constant term of the last coefficient, negative 5. 3 times negative 5 is negative 15. And then you think of factors of negative 15 that would add up, have a sum of positive 2, the middle term, the b. And that would be positive 5 and negative 3. All right, and then I would rewrite that middle term like this. We'd have 3w squared, and then the positive 5, negative 3, I'd rewrite 2 plus 2w as plus 5w, then minus 3w. And then you have the minus 5 equals 0. And then you factor by grouping. You know, the first two terms have a common factor of w. Right? I pull that out. And if I remove a w, then what's left over is 3w plus 5. The next two terms, you know, don't have a common factor, but you know, the lead coefficient in the next two terms is negative. So I'm going to pull out negative 1, right? The greatest common factor is 1, but because the lead coefficient of these next two terms is negative, I'm going to pull out negative 1. And then what would be left over in these two terms when I remove negative 1 would be 3w plus 5. And then you see the whole thing. Both of these products have this 3w plus 5 as a common factor. I remove that. Right? 3w plus 5 comes out. And then what's left over when I remove the factor of 3w plus 5 would be w minus 1. All right, and now I have what I want. Right, I have a product equal to 0. And the only way a product is going to be equal to 0 is if one of these factors in the product is 0. So either 3w plus 5 equals 0, or the other number, the other factor, w minus 1 equals 0. And that would solve these and check these. For this equation, I would subtract 5, giving me negative 5 over here, and then divide by 3. We'd end up with the value of w is negative 5/3. Or, here I would just simply add 1 to both sides. W equals 1. And don't forget to check them. But they should work, right? The original equation didn't have any denominators or that could possibly be 0 or anything like that. Here's the original equation. 1's real quick to check, right? 1 squared is 1. So you have 3 in the first term plus 2 in the second term, 2 times 1. 3 plus 2 is 5, yeah. And then negative 5/3, when you square that, would be positive 25/9. But then times 3 would be 25/3, right? 3 would go into 9 3 times. So you have 25/3 plus, and then negative 10/3, right? 2 times negative 5/3. And 25/3 plus negative 10/3 would be 15/3. And what is 15 divided by 3? It is 5. So both of these work. All right. So that was by factoring, right? I put it in standard form. I found this discriminant to be a perfect square. And if it's a perfect square, that means you can actually factor this polynomial, or at least you should be able to. And I did down here. Right? We got the factors down here, 3w plus 5w minus 1. And then I figured out when each of those was 0 and got my solutions. Now you could have also very easily, if you didn't see or you don't remember how to factor, very well, brush up your skills, practice some more, go back to a section on it, or look up other videos on factoring quadratics and practice. But I find a lot of people tend to remember the quadratic formula pretty well. So if I've already found, I got it in standard form first, of course, you have to have it in standard form in order to be able to use the quadratic formula. I got it in standard form, and then I found the b squared minus 4ac was 64. Well, that's almost half the quadratic formula right there. So let's just put this into the quadratic formula. Okay, so right, I could have done this. If I didn't see how to factor this, we have 3w squared, plus 2w. I have it in the standard form, everything on one side, 0 on the other. And I identified the coefficients, right? A was 3, B was 2, C was negative 5. Then by the quadratic formula, right, again, I'm just going to go QF for quadratic formula. The solutions of this equation will be W equals, the opposite of B, plus or minus the square root of that discriminant, that b squared minus 4ac, which we already found, and then all of that divided by 2a. Alright, so putting these numbers in, the b is 2, right? So the opposite of b here is negative 2, and plus or minus the square root, and I've already found b squared minus 4ac, right? I already found the discriminant. That was 64. Put 64 inside the square root there. Then all of that divided by 2 times a, which is 2 times 3, or 6. Well, the square root of 64 needs to be simplified. I know that that's 8. So we have negative 2 plus or minus 8. And then all of this divided by 6. 6. 2 times 3. And then this is actually, remember, this is two numbers. I know what these numbers are if there's no square root anymore, right? One is w equals negative 2 plus 8, then divided by 6. Well, what's negative 2 plus 8? That'd be 6. And then 6 divided by 6 is 1. Or w could be equal to negative 2 minus 8, then divided by 6. And what's negative 2 minus 8? That's negative 10 divided by 6. But these two numbers have a common factor of 2, right? This is 2 times 5, this is 2 times 3. 2's cancel, and I have negative 5/3. And you see I'm getting exactly the same solutions I got earlier by factoring. And you should, right? I mean, it's the same equation, nothing changed. Alright, so lots to think about there. And you do what you like best. Notice I didn't even do completing the square for one of these, and I probably should have, but just look up a video on the solving quadratic equations by completing the square. But for the most part, I find that the quadratic formula, if you have it memorized, please have it memorized properly as well. If you have the quadratic formula memorized and you put your quadratic equation in standard form, I find that most people have a much quicker and easier time writing the solutions that way than by completing the square, which has several steps involved and is very easy to mess up if you don't know what you're doing. Okay. So I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I have found over the years that when people take the time and the effort to learn something on their own, they tend to remember that thing, that material, for longer, and also remember it better. And they're more proud of themselves for it, for putting in that time and that effort. So of course, read the material, right? Read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can fix your mistakes that way, or learn by some mistakes that way. Of course, do plenty of exercises, practice problems, look for solutions to those whenever they're made available to you, so you can check your progress, check your work. And don't just give up on a problem after the first attempt or two. Don't give up so easily. Very often in mathematics there are several approaches that'll work for any particular problem. So if after several attempts at a problem, you're still having trouble, I would suggest that you go back and actually read the material again, maybe even a third time. Because if you've been working on some problems, like you should, there's a good chance that you now have a better idea as to what the author wants from you, what the author's asking of you. So then when you go back and read again, or that third time, you'll know more about what's going to be important in the section. You'll know what to look for. And perhaps even some things will pop out at you, or you'll notice some things that you didn't the first time through, and it'll make working on the exercises that much easier. But if after that, if after several read-throughs of the material and several attempts at the problems, you're still having trouble, still not getting it, it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. Alright, so ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online, like this one, or plenty of other ones out there that are better than this one. I assure you they're out there and easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Right? Try to have fun with it. Believe in your own abilities. Believe in yourself, even through times of frustration and struggle and mistakes. Because it's in those times of struggle and frustration that you can learn the most, and learn the most deeply. If you persevere and get through and are able to figure out how to fix your mistakes, you'll remember that material far better and for far longer than someone who just got it right the first time and breezed through and never gave it a second thought. All right. So stay persistent. Keep practicing. Stay positive. And don't give up. And I just know you'll get it. And thank you very much for watching.